Morning, everybody. Great to see you here at Evergreen. Welcome to Code Camp. Before we begin, I've got a few copies of my book that I'd like to hand out, if anyone is interested. The book is JavaScript, The Good Parts, and this one is in Russian. Anyone have interest in the Russian edition of The Good Parts? Yeah, please, come forward. Seriously, anybody want the Russian edition? Sorry, yeah, please come up. And I also have the Italian edition. Anyone care for the Italian edition? Anyone? All right.
Well, then more JavaScript and Italian.
And then finally, another Russian edition. Oh. There you go. And now the part you've all been waiting for, the better parts. So we're going to start this morning with Antoine de Saint-Exupéry. Please pardon my French. He was an aviator. Aviator is what we used to call pilots back when aviation was really dangerous. And it was really dangerous because the planes crashed. And Antoine experienced many crashes over his career and survived almost all of them. Once he was trying to set a speed record from Paris to Saigon, and his plane crashed in the Sahara Desert just outside of Cairo. And he was not prepared for survival in the desert. And so he experienced terrible dehydration, so badly dehydrated that he stopped sweating. His brain became overheated. He experienced terrible hallucinations. Fortunately, he was discovered by someone and rescued who knew how to treat extreme dehydration, and so he recovered. But that experience had a big effect on him. World War II is then starting, so he moves to America and becomes a writer. And he's a brilliant writer. His most famous book is The Little Prince. It's like all the great children's books, it's not really a children's book. It's about an aviator who is stranded in the desert, who is visited by a strange little boy who lives on an asteroid and is suicidal. Brilliant book, very. He also wrote books for adults, and in one of them, he gives us one of the most wonderful sentences ever written. He says, "It seems that perfection is attained not when there is nothing more to add, but when there is nothing more to subtract." Just absolutely brilliant, the symmetry, the insight, just a wonderful thing. And you see this used all of the time, being used to describe architecture or engineering or design, anything which combines creativity and discipline. He was talking about the design of airplanes, but it seems to apply to so many things. And it's especially useful, I think, in thinking about computer programming, because our craft has a particular relationship with perfection that no one else has. Our stuff has to be absolutely perfect, or it goes bad in awful ways. And he gives us some insight as to how to attain that we don't get perfection by adding things, we get perfection by removing defects, by removing the things that make it not perfect. And I think this applies also to programming languages. There's a tendency for programming languages to accumulate a lot of features, and we tend to value the features that we add to languages, but this gives us some insight that we can actually make our languages better not by adding things, but by subtracting their defects. So that gives us the principle of the good parts, which says if a feature is sometimes useful and sometimes dangerous, and if there is a better option, then always use the better option. This seems completely obvious to me, but it seems to be a controversial statement. There are a lot of people who violently object to this. And essentially they're saying, I don't want to use the better parts, I want to use the dangerous parts. You can't make. And I think that point of view comes from a profound misunderstanding, because it turns out we are not paid to use every feature of the language. At the end of a project, there is not a manager with a clipboard who's saying, did you leave out any semicolons? Did you use a with statement? Did you use plus plus? You know, no, that's not what they care about. We're paid to write programs that work well and are free of error. That free of error part is really important. Free of error, when did that become part of the deal? Well, it turns out it has always been part of the deal. In fact, it's the most important part of the deal. But we attain it so rarely that it's easy to forget that that's the thing that we're really going after. And so because we forget that, we start pursuing other goals which actually work against that one. So I recommend that everybody learn as many languages as they can, because a good language will teach you. And in understanding the model that a new language presents, it gives you a new set of tools that you can use to think about what we do, and you can apply those learnings to other languages, and you get better in everything that you do. So it's really good to learn a variety of languages. And they should all be different. Like learning C++ and Java and C#, that doesn't count, right? You know, you're not getting a lot of depth there. You want to try other languages. You want to get into Scheme and Haskell and Erlang, you know, Scala, weird languages which will push you, which will teach you. And fourth, sure. And the language which has taught me the most over my career has been JavaScript. And that surprised me because I began working in JavaScript, hating it. I decided to make the same mistake that everyone else makes. I'm not going to learn this language. I have so much contempt for it. I'm not going to make my mind dirty by understanding it. And it hurts you when you do that. And it hurt me when I did that. And so as a consequence, I made every mistake in JavaScript that you can make. Starting with the worst one, the first one. Not going to learn the language. Terrible mistake. That didn't make any sense. So eventually, I decided, well, I'm going to learn the silly language and figure out what it is. And what I learned completely changed the way I thought about it, because it was not the language that I imagined it was, which started to explain why it had worked so badly for me. And when I understood what the language was actually capable of, completely changed the way I think about it. The other thing which taught me, connected to this language, was a program that I developed called JSLint. JSLint reads JavaScript programs and tells you how you're doing things badly so that you can improve your programs. And when I began working on this program, I knew how to write a parser, but I didn't understand what code quality meant. And the things that I was looking for were the wrong things. And over the years, JSLint taught me how to think about quality in programs. That when you address our craft, thinking about errors and how to avoid them and how to make your programs more perfect, it's a big shift in the way we think. And JSLint turns out it was much smarter about JavaScript than I was, and am. It is really smart. So I wrote a book about my experiences with JavaScript and JSLint called JavaScript: The Good Parts, which is now available in Russian and Italian and lots of other languages. And it came out in 2007 or so. It's been out for a while. And it is still a bestseller, which is extremely rare for software books. Most software books are obsolete before they're published. And this one's still in print, and it's still moving well. And it's because what I identified as the good parts are still good. And it's still useful. And even though the language has been through a couple of revisions since this book came out, what it teaches you about this language is, in fact, still the stuff that you most need to know. Now, it is also a controversial book, and there are a lot of arguments against its premise. You know, only use the good parts. And so, you know, what are those arguments? Well, the first one is, well, it's just a matter of opinion. You say that feature is bad, I say it's good. One opinion's as valid as another, so it doesn't matter. And that turns out not to be true. So I am the maintainer of JSLint. And so I get bug reports from people from all over the world. And every once in a while I get something from someone who says, we have just spent 2 weeks clawing through the mud trying to find this thing, and it was caused by some weird, obscure corner case in JavaScript, and we looked at it for weeks, and we never saw it, and it's caused us so much pain. And we think this is something that JSLint could easily look for, and so you want to do that. And I'll look at their suggestion. If it makes sense, I will incorporate it. Which means if you are using JSLint, you will never go through the hell that they went through. Guaranteed. That's not a matter of opinion. That's a fact. Every feature is an essential tool. I need every tool in my toolbox, even the rusty one with a broken handle. I need all of the tools that are in there. And that turns out not to be true either, that you can write better programs by not using the bad tools. And so if you can write a better program without using the tool at all, then it is not essential. But it's sometimes useful. And this is not wrong, because everything is sometimes useful. You cannot think of anything which is not sometimes useful. There's nothing so toxic, so dangerous, so explosive, so annoying that you can't sometimes find a use for it. Everything is sometimes useful. So when that's your argument, it sounds like it makes sense, and it's something you can really get behind. That's sometimes useful. I should be using it. It's actually meaningless. It's like saying, I should be using it because it exists. Existence and sometimes useful are kind of the same thing. I have a right to use every feature of the language. Okay, at this point, the conversation has changed. We're no longer talking about what's the best way to do our craft of programming. We're now talking about our rights. And when you're talking about your rights, you get righteous, right? I'm fighting the good fight. Except this argument always bottoms out at, I have the right to write crap, right? Do you have the right to write crap? Yes, I do. If I have the right to, and it's just silly, right? Because do you have a right? I don't know. It doesn't matter. What you have, what's more important, is responsibility to write programs that work well and are free of error. And if this argument leads you away from that, then that's clearly a mistake. I need the freedom to express myself. I'm an artist, and the way I express my art is by leaving out my semicolons. Then I need to reduce my keystrokes. Typing doing it the right way takes too many keystrokes. I don't have time for that. We have this sense that the thing that slows us down is that we have to get all of those characters into the computer. But it turns out we only spend that much of our time doing that. We spend that much of our time gazing into the abyss, saying, my God, what have I done? And so reducing your keystrokes is not a good thing if it increases the time you're spending looking for bugs. So if I had a magic formula that I could give you which said, I'm going to increase your keystrokes by a factor of 10, you're going to have to type 10 times more stuff, and I'm going to cut your errors in half, that would be a huge win. You would be so much more productive, so much more effective, so much happier. Unfortunately, I don't have such a formula to give you, but that kind of gives you an idea of what we're talking about. So any style which is based on saving keystrokes is probably counterproductive. It's an insult to suggest that I would ever make a mistake with a dangerous feature. You're saying if I use this thing, it increases the likelihood of making mistakes, but it offends me that you think I would make those mistakes. I know better. And it's not about you, right? It's about future you, that you might forget that you did that thing and then trip over yourself. That happens all the time. Even more likely, there are other people on your team who are going to have to fix your rotten code, and they're going to get tripped up by things that you do. So it's not an insult. It's not about you. It's about how do we all work together to make better programs. Then there's a good reason those features were added to the language. And I can tell you for a fact that's not true. Everything happens for a reason, but that's not the same as saying that everything happens for a good reason. There are all sorts of factors which will cause a feature to get added to a language, which are all independent of whether or not it's really good. So Brendan Eich, who's the brilliant guy who designed JavaScript in 10 days, talks about foot guns. A foot gun is a feature of a language that you can use to shoot yourself in the foot. And he put a lot of foot guns into JavaScript, and he now regrets that. And occasionally he'll admonish people, let's not be adding new foot guns to the language. I don't think he says that nearly often enough, but he does say it occasionally. And there are people out there saying, I have a right to use a foot gun, you know? Boom, look, I almost always miss, look at this, boom. So the purpose of a programming language is to aid programmers in producing error-free programs. That's the whole thing. That should be our focus. That's what the thing is for. We used to think that it was not possible to write good programs in JavaScript. So there's no point in even trying. Just write whatever you want. It doesn't matter. You can't do better than crap. And that turned out not to be true. That it's not only possible to write good programs in JavaScript, it is necessary. JavaScript has so many weird cases in it, so many corners, so many sharp edges. It is so easy to go off the rails on JavaScript that it requires tremendous discipline, more discipline, I think, than any other language. So you have to write good JavaScript in order to have it work. Now, there's still a lot of confusion about Java and JavaScript. You know, occasionally, someone will want to introduce me as a Java expert, which it turns out I am, but I'm usually not invited to talk as a Java expert. I'm usually invited to talk as a JavaScript expert. And it's obvious why there's this confusion, right? Both languages have the same name. It's similar to the difference between Star Trek and Star Wars. Right, that they have the same name, right? They're basically the same idea. You know, like Star Trek, you'll get phasers and photon torpedoes and uniforms and damned regulations. Star Wars, on the other hand, you get lightsabers and blasters, you get proton torpedoes, completely different concept. Sand and chaos. And it's pretty clear that JavaScript is the Star Wars language, right? Obviously. So, so JavaScript offers you a choice. You can either go Jedi, or you can go Jar Jar. And sadly, a lot of our brothers have decided to go Jar Jar. So there are a couple of things that I've observed among our fellowship. One is the fantasy of infallibility. I see this especially in younger guys. You know, think, I've got such mad skills, I can just write crazy looking stuff and it works often enough, that's great, you know. And then I see older guys who suffer from the futility of faultlessness, that they've been doing this for so long, they've never seen it work, it's never gonna work, why even try? Two very different perspectives, but amazingly, they both lead to exactly the same thing, which is danger-driven development, where they're taking unnecessary risks as they're coding just to keep it interesting. You know, does it work or not? Nah, that doesn't interest me, but you know, there are bigger things at stake. You know, I don't have to tell you the semicolon story in JavaScript. Well, maybe I should. So JavaScript was a language that was designed in 10 days as a language for beginners. And strangely, the syntax of JavaScript was modeled after C and Java, which are not languages for beginners. And one of the things that makes those languages hard for beginners is the semicolon rule, that there are some statements which end with a semicolon and some which don't, and some which end sometimes and not other times. Like an if statement might end with a semicolon or might not, depending on whether or not there's a block. It's really confusing. And so in order to make the language friendlier for beginners, instead of designing syntax for beginners, which would have been the right thing to do, instead he added a feature called automatic semicolon insertion, which would stick the semicolons in there for you. But it doesn't always work right. It sometimes puts them in places where it shouldn't, sometimes doesn't put them in places where it should, and that's bad. And the way it works sometimes is the parser is going along and it gets a syntax error and it goes, boop, and then it looks to see, is there a line break here? What would happen if I turn the line break into a semicolon? So it'll back up and try it again. And that should freak you out. Like, what? Seriously, is that what's going on? Yeah, that's what's going on all the time. So I recommend, don't do that. Don't do that. That was added to the language for the beginners. So I guess if you want your programs to look like they were written by a beginner, okay, leave them out. But if you're a professional, you will not make that mistake. So one of the things that makes programming so difficult to manage, and in the next session we'll talk a lot more about managing software. First you have to deal with the time it takes to write the code. And it turns out that's really hard to estimate. And one of the reasons it's hard to estimate is that we're usually writing stuff we have never written before, so we don't know, there's no way we could know how long it will take. But the other problem is that we are optimists. We have to be optimists. You can't be a programmer unless you're an optimist. And so we'll think about, well, how long should it take to write that code? That's about that many keystrokes, so da-da-da-da-da-da. And we forget about all of the discovery time that it takes and all of the debugging time that it takes. We just think about how many keystrokes it should take, and that turns out to be wildly off. But then there's the other time you have to consider, the time it takes to make the code work right. Now ideally, that time should be 0, right? You write the code, it should work. And that doesn't happen very often. It's more likely that the time it takes to make it work right is longer than the time that it took to write it. And there are some cases where the time it takes to make it work right is infinite. That happens in projects that get canceled after the code is finished because they never got the thing to work. And that happens still way too often. So if you do anything to try to reduce the first time, which increases the second time, you're doing it wrong. We want to drive the second time to be 0. So we should always take the time to code well. Sometimes if something is only going to be used once or needs to be done real quick, we'll say we'll do it cheap and dirty. And so you just write crappy code because we don't have time to do it right. The fallacy there is you still have to make it work. Right? Even if you're only going to use it once, it has to work once. That means the code has to be clear enough that you can understand it and reason about it in order to get it to work. So you should always write well all the time. So the new edition of ECMAScript came out this year, finally. It was 4 years late, but it came out, and there's some good stuff in it. So I'm reviewing the language and trying to decide what's good in it and what's not. And it's too early to make judgments on all of the features, but there are a few that are good, which have already proven to be good, which I'd like to share with you now. The first one is proper tail calls. This is something that JavaScript learns from Scheme. It's an optimization that the compiler is forced to do, that if a function returns the result of calling a function itself or a different function, instead of generating a call return sequence, it generates a jump. So that means programs will run a little bit faster. But even better, it means that we can reuse the activation of the current function, which means we don't use as much memory, which speeds things up because we're not using the garbage collector very much. And it opens up whole new kinds of programming, like continuation passing style, which is brilliant and wonderful. And with that, JavaScript finally becomes a real functional programming language. And this is brilliant. This is my most favorite feature in the new language. Unfortunately, it looks like it's the last feature that will get implemented. The JavaScript engine makers are listening to you, and none of you are telling them this is what you want. So they've prioritized it last, sadly. Another thing that we've got, which is also very good, is the ellipsis operator, the dot, dot, dot. It's also known as the rest operator or the spread operator. Man, that's, I don't know, is there anything we can do about that? No, I guess not. Okay, so anyway, that's the curly function. And it takes any number of arguments in either the first function or the second function. And down here is most of how you would write the thing in ES5, which is just appallingly awful. There's all sorts of code in here which has nothing to do with the curly function, which is just dealing with the fact that the arguments array was a really badly conceived feature. The dot, dot, dot thing is so much nicer to read and so much more expressive. So that'll be my second most favorite feature. This doesn't allow you to do anything that you couldn't do in the old language, but if you're writing functions that deal with a variable number of arguments, it makes it so much cleaner. Then modules. We have a module system in JavaScript, hooray. So historically, JavaScript has all been about a common global object, which was terrible for reliability and even worse for security. So now we've got a module system which we can call in code and allow it to export a value which can then be imported by another module so that modules can deal with their own linkage, which is great. By getting us away from the global object, it means we can start reasoning about the security of the language in a much more effective way, so that's great. Unfortunately, the syntax and the model behind the module system is way, way too complicated, but there's a subset of it. There's good parts of the module syntax, which is minimal and just does what you need, and that's a good thing. We have let and const in the language, which do what the var statement used to do, except it will respect block scope. So we now have block scope in the language, which is a good thing. Now, it turns out you don't need block scope in a language. You can write good programs without having block scope. The problem was that there are a lot of people coming to JavaScript from languages that had block scope, and JavaScript's syntax is the same as those languages. And so people come to JavaScript thinking it has block scope, and it doesn't. So whenever you have that kind of confusion, where people think it's doing one thing, but it's actually doing something else, bugs happen. And so by having let in the language, we can now have conventions that work for everybody. And that's good. That should reduce error formation, and that's great. Then we also have const. Const is the same as let, except that you cannot assign again to that variable name. So you can only do it once. And in fact, there is a school of programming which says that's the one you want to use. You only want to be using const. You don't want to be using let at all. You don't want to be mutating your variables. You want to be just making new variables. There is some confusion about what const does, though, that with const, the assignment of fas to fax will fail because fax is a constant, it can't be changed. But if it contains an object which is not frozen, you may still change its properties. Okay? Then we've got destructuring. Destructuring is a new syntax. Again, this is a feature that doesn't let us do anything that we couldn't do before, but it makes a few things a little bit nicer to write. So let brace that comma other close brace of some object is the same as creating a variable that it's hard with that cut off, but it creates a that variable which is assigned the value of object.that, and other is some object.other. This will make some things a little nicer to write, but not a big deal. Weak map. Weak map is a really nice feature. What weak map does is it allows us to have things that work like hash tables, that we can have a structure in which we can use any value as the key. One of the design errors in JavaScript is that only strings can be used as keys in objects, and that was a mistake. And unfortunately, instead of fixing the mistake, we added another thing to the language. So the language gets more complicated, and the old thing will never work right, but at least it's possible now. And unfortunately, the new thing was called weak map, which is a problem because it's the worst name ever given to a feature of a programming language. Because nobody wants to put something weak in their program, right? It's just, why would you do that? But it's really good. There's a class of programs that can be written now in the language because we have weak map that could not be written before. So this is adding new power to the language. That's great. Then we've got megastring literals. Megastring literals are written with a backtick and allow you to have a string literal which can occupy many lines. So we can finally get a bunch of stuff. So let me show you an application of that. You're not going to make any sense out of that at all. Even if the screen weren't cut off, you still wouldn't make sense out of that. What that is a regular expression literal which matches all of the new number literals that are in ES6. And this notation is just horrendously awful. Right? You just can't make sense out of it. So something I can do in the new language now is I can say, I can make a function which will receive a string and compile a regex. We've always been able to do that. And it will remove all the white space from the string. And I'll make the string using one of these megaliterals. So I got the backtick as the quote character, and I can now have something that's multiple lines. And I can now add white space to my regular expression. And by adding it in, I can see what the factors are and spread them out, and I can align them so that they make sense. So I can see we now have binary literals in the language, and octoliterals, and hex literals, and in addition to the floating point and stuff that we've always had. So that's nice, right? I wish we had something better than regular expressions, but that's all we've got, and with this stuff now, we can make them work. But I still hate regular expressions because it's such a weird notation, and it's unlikely that it matches what you think it matches, and it worries me that we use them for input validation and security filtering, because who knows what one of these is matching. It's just awful. So there's a tool on the web called Regulex, where you give it a regular expression, and it gives you railroad diagrams. And the railroad diagrams are great for understanding what the thing is doing. And you can get a much better sense of what's being matched and what's being accepted and what's being rejected than you can get from looking at a regular expression. So I recommend this stuff. I will not write another regular expression without running it through Regulex. So this is another new thing that's in ES6, fat arrow functions, or farts for short. So we've got parameter names in parentheses, and then the fat arrow, and then the thing that they're going to return. So the argument in favor of this was function was too long, the word function. That's 8 letters. Are you kidding? 8 letters? We can't type that. That's who's got time for that? And I said, well, there's this new thing now called keyboard macros. And they said, it's too much to read. Oh, okay. So we got that. Also allows you to leave out the word return. So you don't have to type function, and you don't have to type return, and you get this little thing that's a little bit shorter. And for some purposes, it looks kind of nice. Except this case fails. So what this looks like is it's going to return a new object. So I'm going to use it as a constructor, in which the ID property is going to be the name that got passed into the constructor. It's not going to do that. There's a syntactic ambiguity, an intentional syntactic ambiguity that was added to the language, that this will instead return undefined, which, yeah, thank you, yeah, so that's bad. So, we just can't resist adding new bad parts to the language. We could have gotten this right, chose not to. You're going to have to live with it. Anyway, so there are lots of other features in ES6. ES6 is as complicated as the entire language was before, so it adds a lot of new stuff to the language. Again, we haven't had life experience with enough of it yet to know if it was actually good ideas or not. But there is one thing that I'm certain of is a bad part. We already know this for certain, and that's class. Class was the most requested new feature. It was mostly requested feature from Java programmers who are now having to write in JavaScript, who are really annoyed about that, but they're having to do it because that's where the jobs are, and they're unhappy and bitter. And they say, please make it look more like Java because we can't stand this. And so it got added to the language for them. And so they can now write things which look a lot like Java classes and mostly work like Java classes, but in some important ways aren't anything like Java classes. And so when you get into the corners and get near the edge, it's going to get weird and bad things are going to happen. But worse than that is you will never learn how to use this language properly, because what this language is really about is functions. Having nested functions with lexical closure, the best idea in the history of programming. It's in JavaScript, and if you're stuck on classes, you will never learn how to do that. And so the people who are using class will go to their graves never knowing how miserable they are. Every day they're going to be hating this language, not knowing why. So, so after going that, I decided to look back at my book and look at what I thought were good parts then. It's been many years now, you know, has my thinking changed? And some things have changed. So I stopped using new years ago. And in the book, I recommend not using new, that you should use object.create instead. And in fact, I managed to get object.create added to ES5, so it's now in the language, so that I could use it. So I was pretty happy about that. So I was really surprised when I noticed that I've stopped using object.create. You know, it's me, it's my feature, and I'm not using it. And I still use it for the null case, because I like making objects that don't inherit from anything, but that's the only thing I use object.create for. And the reason I've stopped using it is because I stopped using this. And the reason I stopped using this was because of an experiment that I did called AdSafe. AdSafe was an attempt to make a system that we could put third-party code through, mostly advertising, but it could be any third-party code, and automatically determine that it is safe to put that code onto our page, that it cannot corrupt us or navigate us away or steal our cookies or do any of the bad things that third-party code could do in browsers. And there were a number of other experiments at the same time trying to solve the same problem. There was FBJS at Facebook, there was Web Sandbox at Microsoft, there was Kaha at Google, and many others. And one of the really hard problems all these platforms had to deal with was this problem. If you call a function as a method, this gets bound to the object of interest, and that binding is what allows the method to work. But if you take that same function and call it as a function, this gets bound to the global object, which gives away all of our security. And how do you get rid of that? And so what the other projects did was they came up with compilers that would read JavaScript and write JavaScript, which contained lots of indirection and lots of runtime checking to make sure that nothing was getting loose. And that tended to make programs explode in size and to make them much, much slower. My approach with AdSafe was, let's just make this illegal. So if we see a program with this in it anywhere, we reject it. Done. Really easy. And there's no performance penalty. We're just working with a smaller language. And my hypothesis was that the smaller language we're left with is still a functional language. It's still Turing complete, so everything we'd want to do, we can still do. We just have to do it without this. And so, you know, that was my claim. And I decided to test my hypothesis that we don't need this by writing in that dialect. And I wanted to get a sense of, well, how hard is that going to be? How miserable am I going to be? What kind of a tear-off? Because the reason AdSafe never got adopted was that the percentage of existing code on the internet that will pass AdSafe is 0%, right? Because everything is using this, so everything would be rejected. So you'd have to write new code in order to get through AdSafe, and nobody's writing new code, so that didn't happen. But I wanted to test it. You know, what's it like writing without this? And I was really surprised to discover it was easier. It was more pleasant. My programs were smaller and nicer and had more full of goodness, that this was actually making things more difficult and bad. And so just getting rid of this, it was like, wow, that's really nice. So for a while I was kind of recommending, well, you might consider not using this, and now I'm a very strong advocate. We should not be using this at all. We don't need it. Also, having this in the language makes the language harder to talk about, because you can say, this is a problem. So It's like pair programming with Abbott and Costello. So yeah, just get rid of it. Don't need it. Better off without it. I stopped using null. One of the problems with JavaScript is we have two bottom values, null and undefined. A bottom value is a thing which isn't anything. And there's some controversy about whether a language should have a bottom value at all. But there's no controversy. Nobody thinks you should have two of them. And JavaScript has two. And they're kind of alike, but they're not the same. And so if you think they're the same, they're not, and that causes confusion. Confusion causes bugs. That's a bad thing. So we should get rid of one of them. And I decided the one to get rid of is null. Even though it's smaller to type, undefined is the one that the language itself uses. And so it makes sense to go with that one. Also, there's a problem with null with the type of operator. That type of null is object, which is a big source of errors. And if you never use null, you'll never experience that. And so that we were hoping to correct that in ES5 and in ES6 and failed. So that's going to be in the language forever. So it's easier to stop using null than to get the language fixed. I've decided that falsiness was a bad idea. JavaScript is a Boolish language. Every value is either truthy or falsy. And the reason for that was to allow for idioms like C has. In C, this stuff works because it's an undertyped language, so it uses the same value for 0 and false and null and some other things. And so you can just say if something and something will happen. And JavaScript allows you to do the same thing, but it uses the falsy values in order to make that happen. And I think that causes bug formation. Because usually in an if, in a condition, what you're trying to do is to divide all possibilities into two classes. Either the thing that happens if it's true or the thing that happens if it's false. And there are always multiple ways that you could write that condition. And particularly in JavaScript, because we're a loosely typed language, you have to deal with what happens if something unexpected got passed in. So in some cases, you might want to say, if the thing is not undefined, we're going to call it. And if someone passed in something that's not a function, that'll throw an exception, which is exactly what we would have done anyway. So that works. Or if I want, so that gives me an early failure. Sometimes early failure is the thing you want. But sometimes what you want is no failure. You want everything to succeed. So in that case, I would ask, is the thing a function? And only if typod says it's a function, then I call it. And so if they pass in something weird, we don't call it, no harm. Yeah?
I can understand how you create this null because it's falsiness. It might be that got some kind of error in the function and turns out I expected for it to turn false, but it turned 0. Instead, for it to be less easy or difficult to check.
Yeah, one of the big problems with the falsy values is that 0 is one of those values. And sometimes that's what you want. In fact, that's how C does it. But sometimes that's a big problem. If you're expecting null or undefined and you accidentally snag a 0, that's a bad thing. So if you write something as a falsy test, it means that 0 and 1 will behave differently even if the thing was not looking for a number. And
you have to write your own predicate, basically your own predicate parser that sits there and makes sure that your return has true or false.
well, no, I just recommend, in my own coding, what I do is I don't rely on the falsy test. I will say, is it undefined? Is it a function? I will explicitly ask for what the thing is. I don't do the lazy thing, even though I like having lazy expressions. In this case, I think the lazy expression leads you to ruin. So I don't like those anymore. I stopped using the for statement. I found in teaching the language, for is a problem because if you're new to programming, it makes no sense what those three things are in the parentheses. And I find students really struggle with that. And that caused me to ask, well, why are we even doing it like that? But even more than that, in ES5, we added for each to the language and a whole bunch of other nice methods like map and reduce and so on. And those are great. So most of the times that I would want to write a for loop, I use those instead, and the code's just much cleaner and nicer, so I'm not using for. I'm not using for in anymore because I managed to get object.keys added to ES5. So you don't have the problem of inherited properties showing up as you're iterating, enumerating, that instead you just get the own properties of the object and you get them in an array, which you can then use for each on. It's so much nicer. And ES6 will have proper tail calls eventually when it gets fully implemented. And at that point, I will stop using while. I won't use while anymore. I will be using recursion for everything. So here are two versions of the repeat function. The first one is using a while loop. It calls a function until it returns undefined. And the second one is doing the same thing, except it's using tail recursion. So it's returning the result of calling itself. And in ES6, these will both run at the same speed with the same garbage collection pressure. So there's no longer any benefit to using loops over recursion. So I'm going to be fully going into recursion once that gets done. Yeah? No, that's a wonderful thing because this is not a call. It's implemented as a jump. So it's not adding things to the stack. And the compiler will be smart about that. And so you get, these will run at the same speed, same memory. So I've been thinking a lot about the next language because it would be really sad if JavaScript turns out to be the last language, right? I got to think something else is going to happen to replace JavaScript because we can't stop here. This can't be the end of it. You know, if only for our children, right? We need to figure out a better thing to give them, a better legacy than JavaScript. And how will we know that language when it arrives, and what attributes, aspects will it have? It's sort of like looking for the Messiah. You know, what are the signs? How will we know? One thing I'm certain of is that when it does arrive, we will all reject it out of hand because that's how it always happens. And that's because programmers are as emotional and irrational as normal people. We think that we're not, but we are. And most of the things that we argue about with each other, they're really emotional arguments where we think that we are the most rational people in the world, and we're not. We're just like everybody else. So that seems like a rather weird thing to say, but I have many decades of evidence to support this argument. It took a generation to agree that high-level languages were a good idea. Back when people were writing assembly language in the muck, and Fortran came, and you can do the same thing in Fortran, and it's so much easier. And our grandfather said, no, there's no way you can force us to give up our assemblers. You can't force us to use Fortran, even though Fortran was going to make their lives so much better, allow them to be so much more productive. It took a generation to agree that GoTo was a bad idea. Dijkstra published his letter in '68, and for 20 years, we argued about whether it was a good idea, if we should be getting rid of GoTo. And those arguments were violent and emotional, and they just went on for a long, long time. It took a generation to agree that objects were a good idea. Objects were invented in Simula in Norway in 1967. And like all important breakthroughs, the world took no notice of it at all, except for one graduate student at the University of Utah who thought, wow, this could be really good. This could be such an important idea, might be so expressively powerful, we can use it to create a programming language for children. And so he came to California and began doing work on a language called Smalltalk, which was the first modern object-oriented programming language, which has influenced everything that has come since then. Now, the industry had to make a decision what was going to be the standard object-oriented programming language. And there were several candidates. The two leading ones were Smalltalk 80, which is the best designed programming language in history. They spent a decade at Xerox PARC refining and testing this language. Brilliant guys behind it. They got it right. It's just maybe the best thing ever done. And C++. I don't even have to say it, right? I don't even have to say it out loud. You know what it is. And the industry had to choose which way are we going to go. And that decision was made mostly by people who did not understand what object-oriented programming was. And they decided, let's go with C++ because you do not need to know anything about object-oriented programming to use that language. And C++ got some aspects of the object story wrong. And that wrongness got into Java, it got into C#, it's gotten into everything, and we're never going to get rid of it. And then finally, it took 2 generations to agree that lambdas were a good idea. Lambda was the thing that was first inspired by Alonzo Church's lambda calculus, which got into Java, got perfected in Scheme, the best idea in the history of programming languages. And like all the really important ideas, the world took no notice of it at all when it was discovered. And that one took not 1 generation, but 2 generations for us to finally pick up on. And it took so long that a lot of people took that as evidence that, well, it was obviously a bad idea, because if it had been a good idea, we would have adopted it by now. And it took a long, long time. But it is so good, and it has finally gotten into the mainstream, and now it's everywhere. And the first language to bring this idea to the mainstream was JavaScript. JavaScript, this was JavaScript's gift to us. It was amazing. It was followed by Python and Ruby, and eventually C#, and last year Java finally figured out how to do this. It took a long time, but it's happening now. And the reason it finally happened was because we are now doing asynchronous programming, large scale and small scale, because that's the only thing that scales. You have to be able to program asynchronously, and functions provide you the tools that you need in order to do that. And so we're using it, and it's great. So the reason these things take a generation is because we don't change minds. We have to wait for a generation to retire or die before we can get critical mass on the next idea. I lived through the GoTo transition. And I remember we had the violent arguments going on, GoTo is an essential feature. It's how I express myself. We have a tradition. My grandfather used GoTo. You can't, it's so much more efficient. All the other things don't make sense. I've never seen the need for structured programming. Why do we have to change? All those sorts of arguments. And I still hear those arguments today in other things, and they're always bogus. But they sound like they make sense, and we get really righteous about arguing them. And it turned out in the case of GoTo, they were all completely wrong. The fundamental idea was that GoTo, while it has some expediency that I'm here, I want to go there, boom. So it looks really easy. It produces code which ultimately is unmaintainable. You get the rat's nest, the spaghetti code. It's hard to keep track of what's going on. And by getting rid of it and replacing it with structured concepts instead, code becomes easier to reason about, which means that we can increase the complexity of the program to a greater extent before it fails than we could if we're using GoTo. And so GoTo made it easier for us. They were not a benefit to anybody else. They were only a benefit to programmers, and the programmer said, no, there's no way you can force us to do this. So I'm thinking about the next language and where it's going to fit and what it's going to look like. And I want to divide all languages into 2 broad classes: systems languages and application languages. A systems language is something that you would use to write a kernel or a memory manager, a device driver, something really low level, and nothing else. Everything else should be written in application languages. And I want a really clear distinction. And we need new systems language. The dominant systems language today is still C, which comes from the late 60s. We have lost the ability to innovate in systems languages. It's appalling. We should have a better candidate by now, and we don't. But I'm more concerned right now with the application language, because that's where we live, or most of us live. And one problem I see in a lot of application languages is they can't decide which side of this line they're on. So from my perspective, the biggest design error in Java was it couldn't make up its mind. There are aspects of it that want to be on that side, and aspects on this side, which really complicates things for people writing applications. It means you have to deal with threads at the application level, which is madness, but that's a consequence of that. So we can take the application languages and we can divide them into two classes. There's the classical inheritance languages, which contains almost all languages, and prototypal inheritance, which is pretty much just JavaScript. And for a long time, I was a big advocate of the prototypal thing because it's so much easier when you compare it to what you have to do in the classical languages. Because if you're writing in a classical system, you have to do a classification. You look at all of your objects and you figure out what are they composed of, what are they made of, what do they do, and then you have to work out the taxonomy. How are these objects related to each other? What's going to inherit from what's going to implement what's going to, it's complicated. It's really complicated, and it's usually happening at the point of the project, like the beginning, when we have the least understanding of how the system's actually going to work. And so we inevitably get it wrong. That there'll be things in the taxonomy and the hierarchy that we build which just aren't right. And the signs of it start to show up pretty quickly. You find that things don't compose the way you want them to. It's hard. Things that should be hidden have to leak out. That you wish you had multiple inheritance because you can't get there from here. It just doesn't fit. And this brokenness finds its way seeping into all the higher levels. So as you put new classes on top of that stuff, they are broken in a similar way, and it just keeps getting worse and worse and worse. And eventually it gets so bad that you have to refactor, which you don't want to do because it's really scary because it means you now have to stop and tear everything apart and put it back together because sometimes it doesn't go back together. And so you really don't want to do that. And the nice thing about the prototypal model is you never do any of that. And I try to explain that to people coming from Java, say, they go, well, but you have to do that anyway, right? And I say, no, because we don't have these deep dependencies, these linkages, which are the source of all of the trouble. That in JavaScript, everything is light and shallow, and you don't have the dependencies, and so it all comes together really flexibly. And I go, wow, that's really interesting. But you still have to do the taxonomy, right? And you'll still have to do the refactoring. You go, no, you don't have to do that. And I go, wow, that's amazing. But you're still going to write a taxonomy, right? And you're still, no, that, you can say the words, but it's a paradigm shift, and they cannot hear it. And it makes programming so much more difficult if you have to do this stuff. And not having to do that is a blessing. It makes your life so much easier. But you see, most of the people writing in JavaScript are still trying to do this, but they're now doing it in a language without an adequate type system. And so that just increases the pain and increases the misery. So instead, in JavaScript, we got prototypal inheritance. And it comes with some advantages. One is you avoid all of the classical problems. And it provides for memory conservation. So the thing that makes object.create better than object.copy is that each of the instances will use less memory. And that may have made sense in 1995, but it doesn't today. Moore's law has been cranking like crazy on memory capacity. You now have gigabytes of RAM in your pocket. Right now in your pocket, you've got gigabytes of RAM. You cannot even imagine how many bytes that is. It's huge. And the sorts of economies that we think about in what happens in a programming language is dwarfed by how much memory you've got. So worrying about that kind of stuff is in the noise. And so having memory conservation as the primary benefit of your architecture is an indication of some problems. But it introduces other problems. For example, some properties are owned and some properties are inherited. They're kind of the same, but they're a little bit different. That causes confusion. Confusion causes bugs. I don't like bugs. We also get retroactive heredity. You can change in JavaScript what an object inherits after it's been constructed, which I think is madness. I've not found any good reason for that, but there's a threat that at any time objects can mutate in unexpected ways, and that could be really bad. For example, it's performance inhibiting. One of the ways that the makers of JavaScript engines get performance is by making assumptions about the shape of objects. But they have to be pessimistic about prototype chains because there's a potential that a prototype chain can change at any time, which will change the contents of an object in bad ways. So I used to be an advocate of prototypal inheritance. I'm now an advocate of class-free object-oriented programming. I think class-free object-oriented programming is JavaScript's gift to humanity. I think that's why this is an interesting language, why it's worth learning, and why it's working for the world. So let me explain what I mean by class-free programming. So we'll start with the idea of block scope. So in ES6, we're going to get block scope. Here we've got two blocks, and there are curly braces around the outer block. And the inner function can see, or the inner block can see the outer variable, but the outer cannot see the inner one, block scope. All the languages have been doing that since Algol 60. Great idea. And we can do the same thing with functions in JavaScript. We can have a nested function, and the inner function can see the variables of the outer function, same relationship. And that's a good thing. And we can look at the relationship of the functions as sets. So this is the set of variables that the outer function can see, and this is the set of variables that the inner function can see. And we can see that the inner function set encloses the outer function set. And that's why this idea is called closure. And it's sort of unfortunate that we call it closure, because most people think closure means retribution or vengeance. I've been victimized, but I'm going to get me some closure. It's going to feel good. It's not that kind of closure. I wish we'd call it something else, but that's what we're calling it. So we're stuck with that. But it's just the idea that one thing contains the other thing. And the thing that's a little syntactically weird is that the inner thing encloses the outer thing, whereas syntactically the outer thing seems to be enclosing. And that works at the statement level, but at the scope level, it works in the other direction. So again, this is the best idea in the history of programming languages, but it took a long time to get to the mainstream, and it was because of this case. What happens if you have a function that returns a function? So we call the green function, and when we call it, it puts an A on the stack, and then we'll return a yellow function, and then we pop the A off the stack and return. But now you can call the yellow function, and it still wants to go to A, but A is not on the stack anymore. And it took us 40 years to figure out what to do about that. And it turns out it's really easy. Stop using stacks. Put the activations on a heap. You got a good garbage collector, done. Really easy. JavaScript does that, and all the languages are figuring out how to do that now. That's how it happens. And having that, this is the most powerful form we've ever had in a language, a function that returns a function. Incredibly powerful. It is so flexible. You can use it for making everything. It's just amazing. The scheme guys figured this out first, and now we can do it in JavaScript, which is wonderful. So this is how I recommend making objects now in the new language. So I've got my constructor function. I'm going to pass in a spec object, which could be an object literal, or it could be the contents of a JSON message. Usually you see constructors written with a lot of arguments separated by commas. Some years ago, I wrote a constructor that had 10 arguments. And it was a problem because nobody could remember what order they went in. And then we noticed nobody was ever using the third one, but we couldn't take it out because that would break everything. If instead I said, pass in an object literal, that essentially gives you named parameters. By typing 2 extra characters, a pair of curly braces, which you should be used to typing all the time anyway, you get named parameters, which means that we can add new parameters over time. We can ignore parameters that don't make any sense. It doesn't matter what order they're in, much more flexible. Then I'm going to create my member variables. Here, that's a shorthand for saying member equals spec.member. So I can initialize my instance variables in this very clean syntax. And if I put more names inside the curly braces, I can create more variables and initialize them all at the same time. Then if I want some inheritance, I can call some other constructor. I could even pass in the same spec object, so the user of this one will add extra parameters that we don't need that the other constructor might provide. And it will return an object, and then we will pull methods out of that object and put them into our local variables. And we can call as many of these as we want. So if we want multiple inheritance, we can do that, because this is more compositional style than an inherited style. Then we can create our own methods, and because of closure, our methods will have access to this other method in the spec object, and we do not use this, which means we can extract any of those methods, use it as a callback, and it works exactly the same. It doesn't break. Then I'm going to freeze the outgoing object, and in the outgoing object, I'll simply list all of the public methods, and we have a new object literal syntax where instead of saying method colon method, I can simply say method. So it looks more like a nice little list. And by freezing it, it means we get a very high level of integrity, that we have an object which cannot be constructed or tampered with or confused, that its internal state can only be accessed through its public methods, which is exactly what you want. We've never been able to do that in this language until now, but now we can. So we can finally write good, solid objects. I'm always concerned about what happens if we're having to share code with a third party, because we're doing that more and more now as we're getting all mixed up. And this works brilliantly for that. But I'm always thinking in terms of security and also thinking about attacks. And attacks are not always malicious. A lot of attacks are accidental. And this will defend us against those as well. So I need to confess, I made a bug. I'm going to tell you about a bug I made in 2001. I wrote the first JSON parser in Java and open sourced it. It's on GitHub. It's been there forever. And in it, I had this statement. I created a variable called index, which is counting the number of characters we're looking at in the string or the stream that we're parsing, so that if we get an error, we can tell you at what character position the error was detected. And with an int, you get 32 bits, so that gets you about 2 billion characters. And that was a big disk drive in 2001. And I thought, yeah, this is pretty good, because all the JSON texts I was making were only a few K in size. So I thought, this is future-proof, right? This will work forever. So 2 years ago, I got a bug report from someone who was trying to parse a JSON text which was several gigabytes in size that contained a syntax error past 2 gigabytes. And so it reported a wildly wrong number for that. And they were able to very quickly figure out what went wrong. And the thing was that I made a mistake. And the mistake I made was I used an int. I hate ints. I think ints are the cause of a lot of misery in the world. An unnecessary cause. We don't need them. And the thing that's bad about ints is what happens when they overflow. So, let's ask. So what should happen if you try to put a value into a cell in memory that doesn't fit, or the value is too big to fit into memory? What should happen? There are several schools of thought. One school says the machine halts. That's a little old school. You're not going to get to 9 nines that way, for sure. But at least you're never going to compute a false result, right? And that used to be an important thing. Another thing you might do is raise an exception. Fault, something happens, and then allow something to recover from that. So you did something wrong, deal with it. Another might be, we'll produce a NaN value, so that you can then later look at that cell of memory, and it'll tell you, I don't know what you're looking for, but it ain't here. Another thing you might do is instead store the biggest thing that does fit. This is called saturation, and that can be a reasonable thing to do in computer graphics and signal processing, but you don't want to do that in financial applications. I think the worst possible thing would be, we'll simply discard the most significant bits and not tell anybody. If what you want to do is to maximize the occurrence of errors, I think that's the policy you go with. So why do we do that? How did that happen? You have to go back into history. So computers used to be built out of vacuum tubes. And vacuum tubes were big and heavy and drew a lot of power, generated a lot of heat, and would burn out fairly quickly. So they made computers huge. You know, a computer could fill a room like this back in the 50s. And so if you could figure out a way to reduce the number of tubes in your design, that was a huge win, because you'd reduce the cost of the machine, the cost of manufacture, improve the mean time to failure, all of those things get better. So some genius, I do believe he was a genius, figured out if we use complement arithmetic instead of signed magnitude, we don't have to implement subtract in the ALU. All we have to do is complement the input to add and ignore the carry. And that was brilliant. That was brilliant. That made so much sense in the 50s. And we're still doing it. We can't stop doing it, even though it stopped making sense a long, long time ago. Making it worse, they come in a confusion of sizes now. And the reason for that is that memory used to be really expensive and rare. You know, mainframes used to have memory made out of core, where a bit was literally a tiny ring of iron that had wires woven through it. And they'd have women sewing planes of memory. And they were huge and couldn't hold very many bits. They were really expensive. And then we kind of started over with microprocessors. So anyone remember the Atari 2600, the VCS? That machine had 128 bytes of RAM in it. The guys who programmed that machine were heroes. They did amazing stuff with very, very little memory. And so when that was your programming model, yeah, you didn't want to spend more bits on a number that you needed to. But it's not like that anymore. You know, you've got gigabytes of RAM in your pocket now. So if you're in Java, you've got byte, char, short, int, float, long, and double. So every time you create a variable or a parameter or a property, you have to ask, which one of those? And if you pick the right one, then the program's going to work. And if you pick the wrong one, it's going to fail. And your tests will not find it. Your tests will never find it, because the assumptions in your tests assume that all of your variables are big enough. And so your model doesn't anticipate that things don't fit. And so it's going to go wrong. Maybe not now. Maybe it's not going to fail until Christmas, but it's going to fail. And the reason we've got the different types is so that you can save memory. But the value of the memory that you're saving is much less than the time you're wasting trying to figure out which one you're going to do. Now, JavaScript, on the other hand, gets closer to right. JavaScript only has one, which is a huge improvement, which means that you cannot make a mistake choosing the wrong number type. So that avoids a large class of errors, which is great. The only problem is it's the wrong type. And the reason it's the wrong type is because of this. This is the most reported bug in JavaScript. 0.1 plus 0.2 is not equal to 0.3. And the reason for that is that we're using binary floating point. And it's hard to charge JavaScript with that bug because every language designed in the last 20 years has exactly the same error in it. It comes from the IEEE floating point standard that was developed at Intel. And it's binary, and the problem with binary is that it doesn't work for decimal fractions, which is only a problem if you live on a planet that uses the decimal system. But that's kind of the planet that we're on. And so it's not fit for humanity. So how did that happen? Well, again, it's something that made a lot of sense in the 50s. So in the 40s, when the first von Neumann machines started coming online, they were all fixed point machines. Assigned magnitude integers, that was all the machines knew how to do. But they needed to be able to do real computation. And so they started doing scaled arithmetic. And that gets really complicated because you have to be multiplying and dividing things and keeping track of what scale you're at. It was very buggy. So someone figured out that they could put the scale factor in a thing next to the number and have subroutines which would automatically deal with that stuff. And they call it floating point, because essentially you've got a number which tells you where the floating point, where the decimal point will be in the other number. And it was brilliant. Programs became much easier to write, but the libraries were really slow. So there was a lot of interest in figuring out how to get floating point into hardware. So in the 50s, they start working on it. Whoops, sorry. They start working on that, and some genius, and I do believe he was a genius, figured out that if we have a binary basis instead of a decimal basis, then we don't have to implement divide by 10 in order to do scaling. We can do a shift by 1, which is free. And it's like, wow, that makes so much sense. Now, and for scientific computation, that worked just fine, because usually in scientific processing, the lowest decimal places are probably wrong anyway, so it worked. It didn't matter that they're approximating decimal fractions. But the business guys could not use it, because when you're adding up people's money, people have a reasonable expectation they're going to get the right sum, right? And you can't get that with binary floating point. So they had their own system called binary coded decimal, or BCD. So when you ordered your mainframe, you would order either the floating point ALU or the BCD ALU. And each would come with a different programming language. If you're doing scientific stuff, you'd be writing in Fortran. If you're writing business stuff, you'd be writing in COBOL. Eventually, COBOL fails, and Java replaces it. But Java comes from the Fortran school, not from the COBOL school, and Java doesn't know how to do arithmetic correctly because it's using the Intel format. And so everything's wrong, and we're still doing things wrong. And it doesn't look like we're ever going to get it right. IBM was proposing a decimal format, but it is so bizarrely complicated, it looks like it's never going to get adoption. And it doesn't have to be complicated. So I'm going to fix it. So here's how I'm going to fix it. So this is a new format called DEC64. The inspiration comes from what was happening on the EDSAC back in the 40s, that this is basically taking their idea and putting it in a modern architecture. So in a 64-bit word, we have two integer quantities. One is the coefficient, and the other is the exponent. And the exponent determines where the decimal point is. So instead of having a 2 here, we've got a 10, and so we get all of the correct values. And so it's really easy to understand what's going on here. You know, that is it. That's the entire definition of the format. I put the exponent there at the bottom because it's an 8-bit thing, and on Intel architecture, we can unpack that for free. That comes at no cost. We can take any existing int and turn it into one of these simply by shifting it 8 spaces, 8 bits. So it maps very nicely onto what we're doing. It's a decimal basis, so everything comes out exact and nice and good. And I'm going to propose that this be the one number format in all future application languages. That having the confusion of int types is just screwing us up. We would be so much better with this. In a software implementation, which you can get today on GitHub for x64 machines, we can add integers in 5 instructions, which is pretty good, because we're also getting nans and overflow in those 5 instructions. So that's a good value. And other things will be slower, but the things that we do most often will be very, very fast. And a hardware implementation could be even faster. So in hardware, most things will add in one cycle, which is what we wanted ints for in the first place. So we can get rid of ints entirely. So all I have to do is convince everybody in the world, stop doing the old thing and do this instead.
Are you saying that each byte holds a value from 0 to 99?
No, it's one 56-bit number, which then gets scaled by the power of 10. So it turns out I don't have to convince everybody in the world. I only have to convince one person. And that's the man or the woman who designs the next language. If I can convince that person that they want a language with only one number type and it be a number type that works for humans, that produces the same results that we would with paper and pencil, just a lot faster and more accurately, because that will reduce the likelihood that we're going to make bugs and be confused. then it'll happen. Now, it turns out I have a little experience with convincing everybody in the world to do the right thing. How are we doing? Oh, we're late. How many of you are going to come to my next session? Okay, and who is not going to go to the next one? Okay, let's take a break at this point, and we'll say goodbye to you guys and invite everybody else to come in. Oh, yeah.